Hey, welcome friends, and in this video I will be talking about something different from what I usually talk. This video is about a special discussion, right? So let me start this video by asking you some question. So what if I ask you that why methane is tetrahedral, right? So I know most of you will answer that methane is tetrahedral because it is sp3 hybridized, because the carbon atom is sp3 hybridized, right? But actually this question is not completely correct. Methane is tetrahedral, it is not because the carbon atom is sp3 hybridized, right? Because hybridization is something like a mathematical tool for physicist or chemist. We use this to explain the structure of molecule or the geometry of molecule, but it is a hypothetical thing. Hybridization, this orbital, these are not real things, these are mathematical terms. Why? So then why methane is tetrahedral? It is simply because if you arrange four atoms around a central atom, you can have two possible configuration. Either it should be square planar or it should be tetrahedral, right? And now it is if you know the geometry calculation, you will find that in the tetrahedral configuration, the steric hindrance between all these four groups are minimized, and that's why methane is tetrahedral. Now the mathematical calculation is such that to give you a tetrahedral structure, the orbital hybridization should be sp3, right? If you have any other hybridization that also give tetrahedral geometry, then methane will follow that, right? So it is not necessary for for a molecule to hybridize sp3 for getting a tetrahedral structure, but the tetrahedral structure is due to the minimum energy configuration. It is due to the steric hindrance. So the correct statement is methane is tetrahedral because in this conformation it has the minimum energy, and now to get this tetrahedral geometry, its orbital should be sp3 hybridized. Now you may think why I am telling all these things. So in your interview, this type of question they can ask you, and then you have to uh, answer the question with logically. And I am not telling this. If you read the book of Hui, in the bonding chapter, they particularly mention this topic, that you cannot say methane is hybridized because it is methane is the tetrahedral because it is sp3 hybridized. But my today's topic is not about methane. It is actually, I want to ask you another question, that what about your opinion of getting an alkene which is bent, right? So you all know that alkynes. So alkynes are linear, you all know, because again you will say that because this carbon atom is sp hybridized, and sp hybrid orbital gives bond angle of 180 degree, but it is not that. And I will give you logic that why you cannot say that, right? So first of all, tell me, can an alkyne be bent structure? So I don't know what is your opinion, but the answer is yes. Alkynes can be bent, and that proves that the alkynes are not linear because of sp2 hybridization. It is linear because in this linear configuration it has the highest stability in terms of stereoelectronic point of view. What is means of stereoelectronic point of view? So stereo point of view means in this particular configuration these two groups are farthest from one another, and that steric hindrance is minimum, and also this orbital overlap is maximum, and that is the electronic factor. So the stereoelectronic factor favors this linear configuration of alkyne. Now think about a system, a 8-membered ring, right? So if you have a 8-membered ring where you have a alkyne system, so this is not perfectly bent, but it is it is not perfectly linear also, right? You can write it like this, right? So this is your configuration, but in this case also there is a bending in this at this 2 point, right? So this bond angle is not 180 degree, it is less than 180 degree. Okay, so it is a geometrical constraint. This geometrical constraint is such that it cannot attain 180 degree 180 degree bond angle, right? But most interesting example is not this, but if you have this one, let's say you have a methyl group here, and in this case, instead of methyl, you have a 2 hydrogen and 1 fluorine, right? So when you have this compound, that is 1 fluorobutene, 1 fluorobutene, this compound is actually bent, right? So this compound is actually bent one, and you have structure like this. Now, why this compound is bent? So you know that fluorine is very much electronegative, and that's why its LUMO has lower energy. This is the LUMO of CF bond. So fluorine is highly electronegative, and that's why its LUMO has lower energy. Now let's say this CF bond is in the plane of the board. So there will be also a pi bond which is in the plane of the board. And you see, in this particular, when this is linear, this pi bond is not perfectly aligned. So let's say this is your pi bond. So this pi bond is not parallel to this sigma star of this CF bond, and that's why this electron donation, this hyperconjugation, or you can say pi sigma star donation, is not favorable. But when it is bent like this configuration, now if you draw your pi, so this is your pi, and this is your sigma star. Sorry, you have to draw the correct symmetry. So this is your sigma star, and this is your pi. Now you can see these two are perfectly parallel, so there is good overlap, right? And that's why the bent configuration of this particular molecule, where you have you substitute one hydrogen by fluorine, it is stabilized. Now that means it is not necessary that sp hybridization is important for your linear structure, because here also it is sp, it can have sp hybridization, right? But stability, the molecule will search for stability, and it finds that in this particular configuration it is more stable, that's why it will bend. Now what is the consequence of this? So before discussing that, I would like to draw the molecular orbital diagram of this particular phenomenon. So let's say you have, this is your CF sigma star, right? This is empty, and this is your pi, and this system represents, so this is your energy axis, and this system represents a linear case. So in your linear case, obviously this pi bond will be very strong. That means the energy of pi level, which is field, will be lower, right? It is stabilized because it is not distorted. So this pi bond will be very strong, and that's why the energy gap between this will be high and the overlap will be very less, right? So this you can represent. But when you bend this, so when you have bent structure, so when you have this bent structure, this CF level is same, this is your CF level, but in this case, due to this bending, this orbital will now this type, like so this if you bend this, what happens? So this is your alkyne and you bend it, right? So in this case your uh, two p orbitals will be distorted, and that's why there will be less bonding pi interaction, and that's why this energy of this pi level will increase, so it will be here. So what will be the effect of this increase of this pi level? So this is sigma star Cf and this is pi. Now the increase of this pi level means it is more closer to this Cf sigma star, and that's why this stabilization is more here. So you can see the drop in energy, it is delta E here, and in this case it is delta E dashed. So obviously delta E dashed will be much higher than delta E. So stabilization is higher for this particular system, and that's why it will be bent, right? But what is the consequence of this phenomenon? Now if you know the clique chemistry, so what is clique chemistry? Clique chemistry is like if you have an alkene or alkyne. So let's say if you have acetylene and you have azide, right? So you have this azide, right? This is your azide. Now it can react like this. So actually it will be this one, right? So it will react like this to form you, to give you this 5-membered ring. Okay, so this type of rings you get out of this. Now you can see in the transitions, if you draw the transition state, it will be like this. So this is your transition state, and in your transition state these bonds, if there is, I represent it by R. So let's say you have R groups here. So in your initial case this is linear, but in the transition state these R groups will be bent, because finally it will be a double bond and it will have this 120 degree bond angle. So it will be bent in the transition state. So if you have a molecule which is bent, which is partially bent in its ground state, that will actually lower your transition state. And it is found that if you have a normal alkyne like this, so let's say you have two R groups, this R groups may be methyl or ethyl. So the reaction of this normal alkyne with this azide, and let's say you have this fluoro compound where I said that it is actually bent, it will react much faster. So it will react faster than this. So the reactivity of this fluoro compound is faster than this because it is initially bent. So it has less deformation undergoing the transition state, right? It has less deformation and less activation energy it is needed. And even if you use this 8-membered system of octilene system where you have more bending, then the reaction will be even more faster. So if you arrange, this is A, this is B, this is C, and if you arrange their reactivity with this azide, it will be A will be fastest, then C, and then B, right? Why? Because it is already bent, and so it needs less activation energy for undergoing this reaction. So this type of reactions are very important, and this concept is very important because it is a very fundamental concept, and I'm sure that most of you don't know this, right? So I hope this video will be helpful for you, and if you like the video then give a thumbs up and share this video with your friends, and don't forget to subscribe my channel. Thank you.